Hello everyone, I am Dr. Osman and today's lecture will touch on reaction independence, and we shall also look at a subsidiary relation known as the fractional yield. It's typically quite a difficult concept to understand for first year and second year students, so I suggest you watch this video a number of times until you understand what fractional yield is about and how to treat fractional yield in terms of including it in our material balance calculations. So let's get straight to it. So let's consider the following example. We have three geometric isomers of butane, that is 1-butene, cis-2-butene and trans-2-butene, and they can be interconverted over an alumina catalyst according to the following reactions. Okay, and you can see that these reactions are all reversible, and we have 1-butene going to cis-2-butene, cis-2-butene going to trans-2-butene, and trans-2-butene ultimately reverting back to 1-butene. And they tell us that, okay, so they have 60% of the feed stream being pure 1-butene, and it's converted to a product containing 25 mole% of cis-2-butene. So they are simply giving the composition of the feed and the composition of cis-2-butene in the product, and of course 60% conversion, which is a subsidiary relation, and we can look at an assumed basis of 100. So let's look at a degree of freedom analysis considering the number of variables. Okay, we have our stream variables, that's 1, 2, 3, 4, and of course 3 reactions. So it's 4 plus 3, which is 7. There are a maximum of 3 different components associated with this reaction, with this reactor. So we have 3 balances. We have one independent specified composition, that's the composition here, and a specified flow, our basis of 100 moles per hour, and our 60% conversion. So we end up with a degree of freedom of 1. Now let me draw your attention to this reaction set. Okay, and something seems to be a bit unconventional about this reaction set. As you can see that if we add up reactions 1 and 2, we can very easily end up with reaction 3. Or if we add up reaction 1 and 3, we can end up with reaction 2. So how many reactions are there really in this set? Recall in your previous examples we've looked at a reaction set and some of the reactions were reversible reactions. In this particular example we have 3 reversible reactions. So how many reactions are we actually dealing with here? Are we really dealing with 3 reactions, or is it 6 reactions? Is it less than 3 reactions? So let's move on with this problem and see what we can find. Okay, so even though we have a degree of freedom of 1, which of course indicates that the problem is underspecified, so it ultimately implies that we can't solve for all of our 7 variables. Nevertheless, let's just try and write out our balances and our relationships and see what we can solve for. Okay, considering our conversion of 60%, that's equal to our moles of 1-butene in minus the moles of 1-butene out, divided by the moles in. Okay, and from that conversion we can quite easily obtain the moles of 1-butene coming out. And note that in this particular case we have, okay, this is just a recap of the notation. Okay, so let's now look at our material balances. Remember, our output is equal to input plus VIR, or as is written here, input plus VIR is equal to output. Okay, whatever you prefer, you can write it, but be consistent in your approach. So for 1-butene we have 100 moles per hour coming in, and as you can see, it is being used up in reaction 1 with a stoichiometric coefficient of 1, so that's a -1 there, and is being produced in reaction 3. Therefore we have the following setup. Okay, 100 minus 1R1 plus 1R3, and that's equal to our output. Okay, we obtain a similar approach for cis-2-butene and trans-2-butene. There's of course no input to the reactor of these species. However, they are each being produced in one reaction and consumed in the other. Okay, and this is of course to get our output. Okay, and in addition to that, we also have a stream specification. Remember that N2 of C over the total flow rate N2 is equal to 0.25. That's our mole fraction specification. Now we can use this, and remember that even though our species are changing, they are being converted to different species. We have on either side, we have a 1:1. So we have 1 mole simply becoming 1 mole of cis-2-butene, 1 mole of cis-2-butene becoming 1 mole of trans-2-butene. So we have a balance of reactants, 1 mole of reactants changing to 1 mole of products. So we can actually infer that our output, our total number of moles, N2, is equal to N1. And we can use this information to ultimately solve. Okay, so we can express R1 minus R2 using equation 2. Okay, that's this one here. And we can express R1 and R3 as well, since we know what N2C and N2T is now. And that is ultimately what we need to obtain. So we wanted N2C and N2T, and we've got it, even despite the fact that it was stated that our system was underspecified. So the composition of the outlet stream could be determined, even though none of the rates has been actually calculated. Okay, so here's our problem solved, even despite the fact that we didn't calculate our reaction rates. Now, how was this possible, really? Okay, so the entire complication results from the fact that the 3 given chemical reactions are not independent. Okay, any one of them can be represented as a linear combination of the remaining 2. So if we add, for example, reaction 1 with reaction 2, we obtain reaction 3. So reaction 3 isn't really an independent reaction. Okay, it turns out that the solution to example 2.8, which is the above example, can be easily obtained if we simply considered any two reactions. Okay, only out of the given three. So let's assume that, or let's try and achieve that. Let's say, for example, if we took only reactions 1 and 2, then our balances would look like this. Okay, for 1-butene, cis-2-butene, and trans-2-butene. Okay, it's a similar setup. Input plus VIR is equal to output. And this system, this set of balance equations is actually solvable, and we obtain the same results. Okay, these are our results. If we considered all three reaction sets, we have our 35 moles per hour and 25 as before, and we have 25 and 35 moles per hour for cis-2-butene and trans-2-butene here. So to conclude, in terms of our stream flow rate, the solution remains unchanged. Now, a useful rule of thumb for recognizing whether a reaction is dependent or independent is if each reaction in the reaction network involves at least one chemical species which is not present in the remaining, then the reactions of that network are independent. Okay, that is a very vague rule, and it's not necessarily that easy to pick out using this rule alone. So there are systems of chemical reactions which we cannot apply this rule, and we will need more rigorous methods based on linear algebra to actually establish how many reactions or which reactions are actually independent. Okay, and this will be discussed in a later section. Before we look at reaction independence any further, I would like to introduce another subsidiary relation, and that is a term known as the fractional yield. Okay, note, for multi-reaction systems, apart from the conversion, other supplementary measures of the progress of chemical reactions have been adopted by chemical engineers, such as the yield or selectivity. Okay, so the fractional yield given by Yij of product I from reactant J is defined as the ratio of the net rate of production of product I to the rate of production which would be attained if the entire rate of consumption of reactant J would go towards the production of I. Okay, and fractional yield, okay, it's given Yij is equal to the production rate of a product I over the maximum production rate of product I. Okay, now fractional yield is perhaps one of the most difficult concepts for new students to grasp. So I'd recommend you actually get the definition correctly and make sure you understand fractional yield. Okay, watch this video over and over if you need to, because it's very important and it's very easy to get confused about how to express fractional yield, especially when you're looking at different problems and how the yield is expressed. So we have Yij, our fractional yield of product I from reactant J, is equal to the production rate of I over the maximum production rate of I. Okay, so a yield of 100% means that almost all the reactant is being converted to the desired product. If we have a yield of, let's say, less than 50%, for example, this means that most of the reactant is actually being wasted in undesirable side reactions. Okay, so The yield is a measure of the efficiency of a particular reaction set and also the efficiency of a reactor in promoting the key reaction and avoiding the undesirable side reactions. So let's look at an example. We have polyglycols being produced by catalytic hydration of ethylene oxide, followed by successive additions of the oxide to the resulting glycols. Okay, and this is our reaction set here. We have our monoglycol becoming our diglycol, and thereafter our diglycol becoming our triglycol. Okay, now when 100 moles per hour of ethylene oxide reacts completely in an excess of water, the following product distribution is obtained. Okay, so we have ethylene oxide becoming monoglycol, monoglycol becoming diglycol, and diglycol becoming triglycol. And let's say, for example, that our ultimate aim is to produce diglycol. Okay, and we would like to calculate the fractional yield of diglycol from the oxide. Okay, so as you can see, we have 3 reactions occurring. Not all of these reactions are desirable because we ideally would want the production of only our diglycol. But out of the reactor, we seem to be getting monoglycol as well as triglycol. Okay, so let's look at what the yield is and let's see how we can calculate it. Remember, the yield is the actual production rate over the maximum production rate. They have given us the actual production rate. Okay, so that's 30 moles per hour of diglycol coming out of the reactor. Okay, so that's the same as the diglycol output rate, since its input rate is of course 0. Now the maximum production rate of diglycol can be determined assuming 0 outputs for the other 2 products. Okay, so in other words, we know that in reality we have these 3 reactions occurring, and out of our reactor we have 3 products. But now let's consider the ideal case. The ideal case would be if only diglycol came out of that reactor. Okay, so that's the ideal case. So let's perform a balance on the ideal case, and that will allow us to obtain the maximum production rate, or Rmax, of our diglycol. Okay, and watch carefully how this balance is being written out. Okay, so let's say, for example, the mono balance. We know in reality that 10 moles per hour of monoglycol is being produced. But if we want our maximum production rate of diglycol, then we want to set our output of monoglycol to be 0. Okay, so we set our output to be 0. The input was 0 anyway. Okay, we only have ethylene oxide and water coming into the reactor. And we look at our reactions. Monoglycol is being produced in reaction 1 and consumed in reaction 2. So it's being produced, so we have a plus R1, and it's being consumed, so negative R2. And if we look at the case of the triglycol, if we are setting our output to be 0, so that's our 0 there, that is equal to our input plus our production. And as you can see, triglycol is only produced in the third reaction. It's not a participant in the other two reactions, so we simply have 0 is equal to 0 plus R3. Note that we did not ignore these reactions. Okay, and this is the key mistake that students make when they are trying to obtain the yields, when they are trying to obtain the maximum production rate. They tend to think that it's necessary to pretend that these reactions don't exist, reactions 1 and 3. No, in the balance we take into account all of these reactions, but we simply say that the output of these particular components is 0. Okay, so this is not ignoring the reactions, it is simply stating that the output of certain components in these reactions is 0. So if you stick to this particular rule, you should be fine. Okay, so let's move on. From these balances, we obtain the following relationships: that this R3 star is equal to 0 and R1 star is equal to R2 star. And note that we are putting these stars here, and this is because we want to denote that these are not our actual reaction rates. Okay, these are our R values that we are calculating based on this 0 output assumption for monoglycol and triglycol. So make sure you can distinguish quite easily between reaction rates R and our R star. Okay, so now if we look at our total balance, our oxide balance, we have 100 moles of ethylene oxide coming in, and 0 coming out. Remember, it's assumed that the entire reactant is being used up to produce our diglycol. So from this relationship, we end up with R1 star equal to R2 star equal to 50 moles per hour. And now that we have R1 star and R2 star, we can get the maximum production rate of diglycol. Okay, and that is expressed as RD max, and that is R2 star minus R3 star, which is equal to 50 minus 0, which is 50. Now, why is it actually R2 star minus R3 star? Remember that diglycol is produced in reaction 2, so we have a stoichiometric coefficient of 1, so that's 1 R2 star, and it's used up in reaction 3, consumed, so we have a minus 1 R3 star. Okay, and that will be our overall production rate. So that's our RD max, and as follows, it's equal to 50. So we have our maximum production rate and our actual production rate. Therefore, we can obtain our yield. Now let's look at a slightly more elaborate example. Okay, we have example 2.10. The ethylene oxide is made by the partial oxidation of ethylene with an excess of oxygen over a silver catalyst. Okay, so that's an excess of oxygen there, sorry. So this is our primary reaction. Unfortunately, some of the ethylene also undergoes a side reaction to produce CO2 and water. Okay, so these are our undesirable products. And they're giving us the feed composition. If the feed contains 10% ethylene in air, the ethylene conversion is 25% and the yield of oxide from ethylene is 80%. Calculate the composition of the reactor outlet stream. Okay, and they are telling us the air contains 21 mole% oxygen, and we can assume that the rest of the air is nitrogen. Okay, so there are many specifications and subsidiary relations related to this problem. So we have to be very careful in our interpretation of each of this information. So let's look at our degree of freedom analysis. Once again, we count as normal for our independent variables. We have 3, 4, 5, 6, 7, 8, 9 stream variables plus 2 reactions, so that's 9 plus 2, 11. In terms of our material balances, we have a maximum of 6 components associated with this reactor, and therefore that means we have 6 balances. We were given a 10% ethylene in air composition, and we were also given the composition of the air, so that's 2 specifications. However, remember that we need to be a bit careful with this specification of 21 mole% oxygen. When we look at our overall compositions here, that may change. Okay, so we have 10% of ethylene oxide and 90% air, and of that 90%, 21% is oxygen. Okay, so we are not exactly given the oxygen specification, so we need to perform a simple calculation to account for that. However, we can count it as a specified composition. If we assume a basis, let's say for the feed, a basis of perhaps 1000 moles per hour, then we have one flow specification. Remember that we are given a 25% conversion of ethylene and a yield of oxide from ethylene of 80%, so that's 2 subsidiary relations, and that ultimately gives us a degree of freedom of 0. Okay, so the problem is now correctly specified. So let's look at solving the actual problem. So with a basis of 1000 moles per hour, we can easily get our ethylene flow rate in the feed, 10% of 1000. And take note of the oxygen as well as the nitrogen flow rates and how it is calculated. So we have 100 moles per hour of ethylene, therefore 900 moles of air, and 21% of that 900 is oxygen, so that's calculated here. And for our nitrogen, it's calculated by difference. We are given a conversion of 25%, okay, of ethylene. Okay, and remember that when we are talking about conversion, it doesn't really matter how many reactions we are looking at. Conversion strictly deals with whatever is coming in and whatever reactant is coming in and whatever reactant is coming out. Okay, it doesn't specify how the reactant was converted, in which reactions or any of that. It is simply an input and output relationship, and this is it given here. Since we know what the input is, we can of course get the output, and that's calculated to be 75. And the yield of oxide from ethylene is stated to be 80%. So we have our production rate of oxide over our maximum production rate, and that's 80%. So how do we obtain our production rates? Our production rate is equal to the output of our product minus the input of our product. Remember that our input of product is of course 0. So if we had to find the production rate of oxide, it will be equivalent to finding the actual output flow rate, which is what we actually want. So if we can use our yield equation to calculate our production rate, then we can get our output flow rate of oxide. However, we first need to calculate our maximum production rate in order to use the yield equation. Okay, and that requires more work. And we reason it in this way: the maximum rate of oxide production is attained if all of the ethylene is converted to the ethylene oxide. In other words, when CO2 is not produced. Okay, so in order to produce the maximum amount of ethylene oxide, it would mean that this side reaction, although we say that it occurs but it doesn't produce anything. Okay, that is how we reason when dealing with yield. Okay, so we have 0 production of CO2. So if we write out a balance for CO2, we have the output of CO2 being equal to input plus 2R2, because it is being produced in reaction 2. Of course, there is no input of CO2 in the feed, and if we have an N2 of CO2 is equal to 0, in other words a 0 output of CO2, then it means that our R2 star will actually be 0. So now if we had to calculate or perform our C2H4 balance using this R2 star, remember we have output is equal to input plus VIR and plus the sum of the VIRs, and our C2H4 is being consumed in reaction 1 with a stoichiometric coefficient of 2 and is being consumed with a coefficient of 1 in reaction 2, and here we have it. Output is equal to input minus 2R1 minus 1R2, and as we've previously calculated, our R2 star would be 0 in the case of maximum production rate. We know what our output is. Okay, we've calculated that from our conversion, and so we get the following: our output is equal to input minus 2R1, and therefore our R1 star is 12.5. Okay, so under this type of conditions of maximum yield, we are talking about R1 star and R2 star. Okay, and the same here. So we have not actually found our R1 and R2 as yet. We have found our reaction rates under maximum production of oxide, under those conditions. Okay, so that's our R1 star. And if we look at our our production rate, we'll note that our production rate for our oxide will equal to 2 times R1. So therefore we look at 2 times R1 star, and that is our maximum production rate of oxide, ethylene oxide. So once we've obtained our maximum production rate, we can use our yield equation and get our actual production rate, which is of course equal to our output of ethylene oxide. Okay, so that's our output there. Okay, so once we've done this part, now we can look at our actual material balances of the species in real conditions. So it's very important that you determine the difference between writing a material balance at maximum production rate conditions, okay, in order to make use of your yield equation, and actually writing out our material balances in reality. Okay, and the typical procedure is as follows. Once we have completed our degree of freedom table, we try to make use of our conversion and yield subsidiary relations first, and thereafter see what we can solve for, and thereafter perform our actual material balances. Okay, and this is standard stuff. Our output is equal to input plus the summation of VIR for our two equations, and it would be very good if you would actually look at the diagram and write this out yourself. Okay, it's the same old thing. Output equals to input plus the summation of VIR for each of our components, and thereafter we can solve either sequentially or simultaneously for all of our unknowns in this material balance system. Okay, so we end up getting R1, and this is the actual R1 to be 10 moles per hour, the actual R2 to be 5 moles per hour, and ultimately all of the output flow rates of each component.